Welcome back to the show. Today we are going somewhere that I think a lot of engineers who have moved into AI and LLM work quietly dread. We are going back to fundamentals. Algorithms, complexity analysis, graph traversals, the stuff you crammed for interviews and maybe hoped you would never need again. My guest today is Oguz Koroğlu, and he is going to make a case that not only do you still need to understand algorithms, you need to understand them more than ever if you are building LLM agents. Oguz, great to have you back.
Adam, always a pleasure. And yes, I know that framing might sound alarming to people who have spent last 2 years building AI products without writing a single line of merge sort. But stick with me. This is not a nostalgia trip.
Let us start with a provocation then. We live in a world where LLMs can write a Dijkstra implementation in 30 seconds. Why does a working engineer building AI systems need to understand algorithms at all?
Because writing code and understanding what it does at scale are two completely different things. The LLM will give you a working Dijkstra. What it cannot do is tell you why your rack pipeline is timing out on graphs with 50,000 nodes, or why your agent context retrieval is O of n squared when it should be O of n log n. The moment you are debugging a production problem, you need the mental model, not the code.
Fair point, so let us build that mental model. Start with a foundation, big O notation. What do you actually need to know about it day to day?
The most useful thing is internalizing the complexity hierarchy. Constant time of O of 1, hash table lookup, that is your best case. Logarithmic O of n of log n, binary search, balanced tree operations, then linear O of n, a single pass through your data, then O of n log n, which is where sorting lives, and it is the practical ceiling for most data processing. Then O n squared, and that is where things start to hurt in production. And then exponential and fractional. Those are effectively off the table except for very small inputs. If you have an algorithm that scales with n squared and your input is going to be 10,000 items, you have a production problem.
You said O of n log n is the practical ceiling for sorting. There is a lower bound proof there if I remember correctly.
Yes, and it is a beautiful result. Any comparison-based sort, anything that works by comparing pairs of elements, cannot do better than omega of n log n in the worst case. That is provable by information theory. If you have n elements, there are n factorial possible orderings and each comparison halves the search space. So you need at least log base 2 of n factorial comparisons, which works out to omega of n log n. The only way to beat it is stop comparing, which is what radic sort and counting sort do. They sort in O of n plus key by exploiting the structure of the values rather than comparing them.
When have you actually used non-comparison sorting in production?
On a trading platform, we had a hot path that needs sort A events in by timestamp. Timestamps were integers in a bounded range, milliseconds since market opens, so at most maybe 50 million distinct values in a day. Counting sort brought the sort step from measurable latency to basically zero. Nobody writes counting sort in interviews, but when the conditions are right, it is a genuinely different class of algorithm.
Let us jump to dynamic programming, because this one trips people up even at senior level. What is the mental shift required to actually think in DP?
The mental shift is recognizing that your problem has two specific properties: optimal substructure and overlapping subproblems. Optimal substructure means optimal solution to whole problem contains the optimal solutions to its subproblems. Overlapping subproblems means you are computing the same subproblem multiple times. If you have both, you are almost certainly looking at DP. The classic example is the Fibonacci. New recursion is exponential because you recompute Fibonacci of 500 times, memorize it, and it becomes linear. The conceptual jump from recursive to DP is before computing something, check if already computed it.
And you have used this in AI systems specifically?
All the time. Catching immediate LLM outputs in a pipeline is essential memorization. You are recognizing that the same prompt substring produces the same embedding or completion and storing it. Semantic catching is RAG DP thinking applied to the language. The specific data structure is different, but invariant is the same. Do not recompute what you already computed.
Graph algorithms next, and I want to make this concrete because this is where I see AI engineers most often hit a wall. BFS versus DFS. When does the choice actually matter?
The choice matters wherever the structure of the problem cares about distance or reachability. BFS processes nodes level by level, which means it finds the shortest path in an unweighted graph. DFS goes deep first, which makes it natural for cycle detection, topological sorting, and finding connected components. In agent systems, if you are modeling as a workflow as a directed acyclic graph, which LangGraph literally does, topological sort is how you determine execution order. DFS gives you that. If you are doing retrieval over a knowledge graph and you want the closest related concept first, that is BFS thinking.
Dijkstra's algorithm. Explain it the way you would explain it to someone who needs to use it tomorrow, not pass an exam.
Dijkstra answers one question. What is the cheapest way to get from point A to every other point in a graph when edges have non-negative cost? The algorithm keeps a priority queue of nodes ranked by their current known distance from the source. Each step you take the cheapest unvisited node, and for each its neighbors you ask, is the path through me cheaper than what you already have? If yes, update. Repeat until the queue is empty. It runs in O of V plus E times log V with a binary heap. The key constraint is non-negative weights. If you have negative edges, you need Bellman-Ford instead, which is slower but handles it.
Where does Dijkstra show up in real AI systems?
Anywhere you have a weighted routing or planning problem. In a multi-agent system where different tools have different latency or cost profiles, routing a task through the cheapest sequence of tool calls is a shortest path problem. I also used it in a content recommendation. If you model content item as nodes and similarity scores as edge weights, find the most relevant path through a content graph is Dijkstra. The graph is implicit, but algorithm is identical.
Let us talk about data structures, because I think this is the most underrated part of the foundation. What is the mental model for picking the right one?
Think about what operations you need to be fast. Hash tables give you O of 1, average for insert, delete, and lookup. They are your default when you need a dictionary or set and you don't care about order. Heaps give you O of log n insert, O log n extract min, or extract max. Use them whenever you need to repeatedly pull the smallest or largest element, which is exactly what Dijkstra needs. Balanced binary search trees like red-black trees give you O log n for everything and maintain sorted order. Useful when you need both fast lookup and ordered iteration. Arrays beats everything on cache performance for sequential access. The mistake I see is people defaulting to arrays or lists everywhere when a heap or hash table will change the complexity class entirely.
Union find? I want to ask about this one specifically because I feel like it is a hidden gem that not many engineers outside competitive programming have used.
It is generally underused. Union find or disjoint set union solves one problem extremely well. Given a set of elements, efficiently answer the question, are these two elements in the same group, and efficiently merge two groups. With path compression and union by the rank operations are essential constant time. Technically, O of inverse Ackermann of n, which for any practical n is less than 5. I used it on a microservice dependency analyzer. The question was, given a list of service-to-service call edges, which services from connected component, and does adding the new edge create a cycle? Union find answers both in near constant time per query.
Greedy algorithms, the category that sounds deceptively simple but has a gotcha in it. What is the gotcha?
The gotcha is greedy only works when the greedy choice property holds, meaning locally optimal choice at every step leads to a globally optimal solution. That is true for some problems, and completely false for others. And the hard part is knowing which you are dealing with. Activity selection, for example, picking the maximum number of non-overlapping events, is a classic greedy problem. Always pick the event that finishes earliest. But the coin change problem, which looks similar, is not greedy for arbitrary coin denominations. Forget about it. Coin denominations. People reach for greedy because it's elegant and fast. And sometimes they get a solution that looks correct and small inputs and fails on edge cases. The way I test greedy intuition is to try to construct counterexample before I commit the approach.
Talk to me about the Master Theorem. How often does it come up in real work? We have about 2 minutes.
More often than the people expect, but usually implicitly. The Master Theorem lets you derive the time complexity of any divide and conquer recurrence of the form of t, of n equals a times of t, of n over b plus f of n. Merge sort e equals 2, b equals 2, f of n equals o n. That puts you in a second case, giving o n log n, binary search, e equals 1, b equals 2, f of n equals o1. First case, o n log n. In practice, I use it whenever I am reasoning about the complexity of a recursive pipeline. Chunking a document, processing each chunk in parallel, and combining results is structurally divide and conquer. And the Master Theorem tells me whether my parallelism is actually buying me anything.
I want to end with a question that I think gets to the heart of why you put together a guide called Comprehensive Algorithm Guide for LLM agents specifically. What is the connection between classical algorithms and the agent systems you are building today?
The connection is that LLM agents are software, and software runs on hardware, and hardware has finite time and memory. An LLM agent that retrieves context from a vector database is doing approximate nearest neighbor search. That is fundamentally a graph or tree problem with a complexity budget. An agent that orchestrates the tool calls in the right order is doing topological sort over a dependency graph. An agent that decides which catched response to reuse is doing memorization. The LLM is the new part, the reasoning layer, but the infrastructure around it, data structure and traversal algorithms that make it fast and correct and scalable. That is 50 years of computer science. The engineers who understand both layers are the ones who can build agents that actually work in production rather than just in demos.
Oguz, this has been brilliant. Where can people find the guide and your other work?
The algorithm guide is in my developer guides repository on GitHub. It's synthesized from CLRS and several other textbooks into a format that is actually useful for reference rather than study. My YouTube channel is Beyond the Developer. You are in it. I post production engineering content there, including full microservices podcast that the people seem to be enjoying. GitHub is OGU83, my username in the GitHub. And for consulting and AI integration work, I am a Upwork.
That is Oguz Koroğlu. If you are building anything with LLM agents and you have been hand-waving the complexity questions, this conversation is your sign to go back and fill those gaps. See you next time.